Hello, everybody. So for the Introducing Vector Lab, there were the questions, and one of them gave everybody a lot of trouble. It had to do with what seemed like a rounding issue. And I left that question the way it is so that we could be forced to have this conversation about spatial data and some of the changes that have occurred since Esri switched from ArcMap Desktop to ArcGIS Pro. So in the, 20 times I've taught this class in the past, we've been calculating the length of the Yellowstone River using a projection. The UTM Zone 12, which is the coordinate system that the river or stream data comes in from the Utah AGRC. It's also the projection that we use in Utah, just generally. So I just want to show you a couple of things and get you thinking about some of the limitations and why you need to be suspicious, if not just terribly curious, about the origins of your data and what the data is really representing. So when we isolate the section of the Yellowstone River, this is what we get. We're in the Uinta Mountains. And I think it's, first of all, important to know that ArcGIS Pro now gives us the ability to make distance and area calculations geodesically. And so it's going to ignore the projection that might be applied to the data or the map. And it's going to just use the geometry of the Earth's curved surface to make the most accurate calculations that it can. When we do that, if you can see, I'm in the attribute table down here. I selected the 103 Yellowstone River polylines, and if I go in and statistically summarize them, hopefully this window will pop open. What you can see here is the value that most of you got. It's just over 21 kilometers. We can double check that, and I think it's a really good idea to have an idea in mind when you're going to measure something like this. We can use the measure tool and just get a very coarse idea of the length. And so here it's saying that it is around 21 kilometers long. And so that, that calculation seems reasonable. If we were to use the shape length field that was already in the data set, and this is a really easy crutch to rely on, if we summarize those lengths, then you'll see that we get the answer that's in the answer form, 21,130 meters long. So that is using a projection, and we can test that by making the calculation using the projection instead of using the geodesic. And I'm just going to show you one more time. When you calculate geometry, we can tell it to calculate length or length geodesic. This is going to be, generally speaking, the most correct. This is going to employ a projection. And then we can tell it what coordinate system to use here. And in this case, I just used the coordinate system associated with the stream data. This is appropriate for Utah. And when we do that, we just recalculated the same old thing, and then sum it, we end up with the same length as the shape length field, so 21,130. So calculating geodesically did add 7 meters, a little over 7 meters to the length of this. So they are a little bit different. What is that? 7 times just over 3. So like 22 extra feet. Is that a big deal? Well, let's look at the actual data and see what it is looking like on the ground. I'm going to get rid of this data set and add a base map that gives us satellite imagery. I'm actually also going to turn off this other stream data set because we don't need that. Okay, so I made a couple of bookmarks. Zooming in, here's the polyline that maps the Yellowstone River, but since it was digitized, the river has cut a new swath, and now it's running here on the west side of the floodplain, And you can see it's cut all of this off and is now running a little bit straighter. So we could digitize the length from here to here, and then digitize the length from here to here and compare them. But I think most important, it's just really good to see how a polyline represents the real world, and how many different kinds of disconnect there are. Here's another mapped deviation. So the river comes down here. This whole bend has been cut off and straightened here. And then the channel, instead of running on the east side, is now running on the west side of the floodplain. It's arguable whether it's longer or shorter. Here, it's now adding a little bit more distance. So what's the answer? I think the take-home message here is that a polyline can only represent reality as well as the scale that it's created at. So if you were interested in studying this river, you would go in and manually digitize the center line or maybe the banks, and then you could perform your own calculations on it. If you had aerial photos over time, it's a really common analysis to measure stream migration by comparing locations of center lines as they migrate over time. So adding on to that, my third bookmark here takes us to the top of the polyline. So this is where the Yellowstone River starts. I'm going to turn this off. So you can see that, is there anything substantially different about the river from here or here? Here it's called the Yellowstone Creek, and the creek runs way up. So this is all considered Yellowstone Creek. So, you know, at what point does a river start? At what point does a creek become a river? That's another somewhat, I'm sure there's a hydrologic reason, but another somewhat arbitrary constraint on our spatial data. So I'm the one who asked you to calculate the length of the Yellowstone River. The reason for doing that is because I wanted you to get more comfortable working with the attribute table and doing select by attributes, and getting more practice doing calculate geometry. But I want to point out all the nuances that are associated with that and the real limitations of something like a polyline representing a real, movable, flexible, you know, living entity like a river, whose course is going to change over time. Yeah, so I hope that helps a little bit. When you calculate, getting back to the answer form, when you calculate the length of the Yellowstone River geodesically, it does round to 21,140 meters. If you were to use the UTM projection, which is completely appropriate, it's 10 meters less. But what does that 10 meters mean? And then the real question is, well, how much should we be rounding our results? You know, is rounding it to the nearest 10 meters appropriate, or can we account for more than 10 meters of uncertainty along a polyline like this? These are questions that we spend a lot more time delving into in the advanced class, but you should definitely be aware of some of these limitations of spatial data and how it relates to scale. All right, thanks.